This is a bromination example for the alkene addition lab. In this lab, you'll be using cinnamic acid as your reactant, so I've drawn that here, including stereochemistry. When looking at this molecule, it's a little overwhelming just because there's a lot going on, so let's break it apart a little and understand the functional groups and where exactly the bromination will occur. So when I first look at this molecule, I see a functional group here, and that's carboxylic acid, or COOH. I also see a functional group here, and that is our benzene. So hopefully these are familiar to you. And when I remove these, our groups, we're really just looking at butene, which is a 4-carbon chain with a double bond. Here's our double bond. So we're looking at a simple molecule if we remove those R groups. And that's what I want to go through for our bromination. So E-but2-ene, E because of that EZ configuration, these carbons on opposite sides. Butene because of this 4-carbon parent chain. And 2 because that is where our alkene starts. So that's just a review on nomenclature. So that's our molecule there. I've drawn out Br2 with its lone pairs so that we can accurately show that arrow pushing. But you might be thinking Br2 is a nonpolar bond. So how exactly does it become an electrophile? As Br2 approaches our molecule, there is an induced dipole-dipole. So the one Br becomes partially positive, and the other becomes partially negative. So the electrons are being pulled towards that partially negative bromine. And this allows for a nucleophilic attack. So for simplicity, I'm just going to label this as bromine 1, and this is bromine 2. So now that we have our electrophile, our alkene serves as our nucleophile. So our alkene is going to go out and grab that bromine, and that will kick up electrons onto bromine 2. And then because of that, we've created a bond here now with bromine. So that's our imaginary bond. And we now have a partial carbocation at this carbon here. So these electrons from bromine 1 are going to go out and grab that. And that's how we get 2 bonds to bromine 1 here in our intermediate. So that's important to understand. I'm going to label this is bromine 1 that is now attached and a part of this intermediate, and this is bromine 2 off on its own, and it has a negative charge because we gave it, or it gained electrons through that bond breaking, and bromine 1 has a positive charge because it lost electrons to bromine 2. Okay, so next, our bromine 2 is our nucleophile, and it is going to attack that carbon, kick up electrons onto bromine 1, and now it has attached itself to our molecule. So here you can see bromine 1, here let me label, bromine 1 and bromine 2 are both attached to our butene, including stereochemistry. It was a backside attack, so we have this bromine facing away, and we have an enantiomer. Whoops. We have an enantiomer here. And I just want you to take a second. I'm going to pause. Think about why there is an enantiomer. The reason we have an enantiomer is because the bromine could attack. Oh, sorry, that's not an accurate arrow. Bromine can attack that carbon, kick up electrons, and this bromine 1 would end up on the other side there. So we have the opposite stereochemistry as well. Is it syn versus anti-addition? In this example, I believe this is one of your pre-lab questions as well. This would be anti-addition because the bromines are being added to opposite sides. So you can see they are both on opposite sides there. So anti-addition. So hopefully this helps you kind of walk through bromination, and you're able to do it with cinnamic acid during lab. And just make sure you ask your TAs if you have any questions.